Excellent. I think we can we can start. I would like to warmly welcome you to this showcase session for the EIC Pathfinder. And I'm very happy to see a full room, so a lot of interest in the activities that are currently taking place under the EIC Pathfinder pilot. My name is Martin Lange. I'm Deputy Head of Unit for FED Open, which is basically the bottom-up part of the EIC Pathfinder pilot. And the aim of this session is basically to show you a number of projects that we are currently funding that is aiming to basically carry out research for future technologies. With this number of presentations and the distinguished speakers that we have here, we would like to demonstrate to you that actually Europe is actively developing these kind of future technologies, and I'm very delighted also that you will learn more, at least in this first part of the session, on new materials, about the holy grail of laser technology, for example, about magnetic nanoparticles and how they can be used for thermoelectric energy generation, or also a new type of disruptive solar cells, perovskite, based on perovskite materials. But this is, I think, enough as an introduction. And I would like to call the first speaker. This is basically Mr. Philippe Potti. He's a professor of microengineering and the group leader for medical devices at the Haute École Arc in Switzerland. Philippe.
Phone is working? Yes, now, yes. So I will not continue this presentation. I believe it has been done. Thank you for coming. And we are experiencing the first technical difficulty here. Yeah, I'm pushing the green button.
Just put your port button now.
All right, thank you. So it's a privilege and my pleasure to present here the work of the scientists and partners of the Magenta project. Energy is key. From powering the devices to explore deep space, where every kilogram matters, communicating devices for the Internet of Things revolution, smarter medical devices to boost treatment efficiency, achieve better patient care, and increase cost effectiveness, and to power all the electronics to treat the exponentially growing signals that will form the backbone for all this. Where do we get that energy from? Of course, we can produce it from fossil resources, but can we harvest it from our surrounding environments? So energy harvesting is that process, is the process of deriving instead of producing energy from surrounding environment. Ambient sources, such as solar energy coming from the sun, we are very familiar with those technologies. Doesn't work on the screen. I'm pointing at the solar panels on the right, on the left side of the picture. Then, of course, well, we know the wind turbines and the wind farms, and we also know the kinetic energy that we get from transforming the energy we store in the dams into hydraulic power plants. So with these energy harvesters, we will actually produce small amounts of electricity that can be captured and stored to be used in those small, mobile and autonomous devices that we have seen before. Now let's concentrate as heat as our ambient source of energy, and I'm sure that everybody knows about that heat engine. It is the steam engine, and of course we know how it works. We warm up water, it transforms into steam, steam expands, it pushes on something, then steam condenses, and it will let that something, maybe the piston, shrink. We have achieved mechanical movement. And it can be repeated. So we produce movement. It can be transformed as well into electrical energy. Or we can also harvest electrical energy immediately. There is a key concept to to keep in mind when it comes to heat engine and heat harvesting. We need to have a difference in temperature. The temperature on the outside of the train is to be colder so that the steam will condense and let the piston come back so that we can achieve the movement. So all the heat engines and thermoelectric generators work on that principle of a difference in temperature. If you can launch the video, fantastic, thank you very much. So in 1821, Seebeck discovered that when we apply a temperature difference on a conductor, the heat will flow from the warm to the cold area, and also the electric carriers will flow, generating in turn a difference of potential and a current. So in this example, unfortunately I cannot really point it, but between the two arms of the device there is that white element which is transforming the difference of temperature between the two arms of the device plunged into the cold and the hot container, and that's transforming the difference of temperature into enough electric energy to power that fan. So if you Google the Thermoelectric Effect demonstrator, which you can buy actually on Amazon or something like that, you see the whole demonstration where the operator will actually pour the warm water into the hot bucket, and then if we leave it long enough, we will see that the fan will stop because the difference of temperature will actually disappear. The temperature will equalize. The funny thing is, if we start with water at the same temperature in the two buckets, and we would spin the fan by hand, one bucket will grow warm and the other will grow cold. So that's how we use today the Peltier or the Seebeck effect. Can we go back to the, yes, thank you very much. To achieve good efficiency though, specific materials are required. And today, most thermoelectric materials, thermoelectric components, are based on bismuth telluride. And it's a bismuth telluride semiconductor, which is sandwiched between metallized ceramic plates so that you can transport it. However, tellurium, which is one of the two components, is very rare and toxic. Toxic for the environment. So I'll let you imagine the impact also on its price. So because of the environmental concerns and because of its cost, further progress of that technology are seriously hindered. The very last development in this form of thermoelectric generator is the nanostructuration of the surface to extract as much electrical power as we can from a difference of temperature. But that process of nanostructuration is complex, is expensive in itself, so it's limiting the development of the technology. And here comes Project Magenta and its challenge, which is identifying new thermoelectric materials that are not toxic, more abundant, and efficient. So we have based our research axis on the liquid thermoelectrics, and more specifically on the magneto thermoelectric liquids. And those are ionic liquid-based ferromagnetic fluids. It's a suspension of nanoparticles in fluids, and they seem to offer all the characteristics for high efficiency, meaning that they can actually convert small differences of temperature into high electric power. So we are talking about ionic salt or ionic liquid, and basically those are salts. That will be, this is kitchen salt, the one you know, and actually those ionic liquids are salt that are liquid at ambient temperature. So we know, we both know, we all know that salt, this one, melts at 800 degrees, which is good for kitchen. But when it melts, it's mostly composed of pure charge carriers. So it's Na plus and Cl minus charge carriers. So they're extremely powerful electric conductors. plus, because many of these ionic liquids are very not volatile, this is one less vector for the contamination of the environment. So today, in the Magenta project, we have already realized a demonstration and a testing cell, and many of these ionic liquids have been characterized and evaluated for different types of applications, understanding at which temperature they will work and for which usage they can be developed. And today, with one single microcell, I will come back, you will see a picture later, we can generate a difference of potential of 1.5 millivolt per degree of difference. So 1.5 millivolt. So you will tell me that's not much. Yeah, that's true. That's not much. But we need to consider this. Those microcells are extremely tiny. We are talking micrometric scales. So we can put hundreds of them on small surfaces. And this is an example with 36 of those little cells. Now, one of the goals of the project is to produce a prototype that would include 100 of these microcells. One microcell is really only one little circle there, one little hole. And if we consider that example where the working temperature of an exhaust pipe in a car is about 300 degrees, and the ambient air temperature is about 30 degrees, we know it's going to increase over time. Not much we can do about it, but so the difference of temperature is about 270 degrees, and the electric potential we would get with one single chip of 100 microwells would be about 40 volt. And with those 40 volt, you can already power the car subsystems, or you can use that energy to recharge different devices that would be plugged into the car. Today, that energy is completely lost. But there is more. This is one example of the soft thermoelectric generator that can be achieved because the thermoelectric material is liquid, so it can be bent. And with the new microfacturing process, such as bonding, it can be embedded into medical devices, for instance, for powering and communication. So this is the last slide. So today it is too early to say that those liquid-based thermoelectric generators will be able to harvest enough energy in real time to relieve the need for batteries. But still, we believe that it's constituting a solid platform for the transformation of the energy paradigm and offer a sustainable energy source. Thank you very much.
Thank you very much, Philippe. I'm sure you have plenty of questions, but unfortunately we are running a little bit short of time. We have 5 other presentations coming up that will unfortunately not allow us to go into the details, but the speakers will be available after the session as well, and maybe at the end, if we have some time, we can still take 1 or 2 of those questions. So let's go straight to the next showcase. Now we come to the project SILAS, and the coordinator of SILAS is Jos Haverkort. Jos is associate professor at the Department of Applied Physics from the Eindhoven University of Technology, and he will tell us all about his developments regarding silicon-based lasers.
Okay, thank you very much. And how do I get to the slides? Okay. Okay, I'd like to introduce to you the SILAS, or the Silicon Laser Project. And what you should know is that developing a silicon-based laser has been a holy grail for many decades in the semiconductor community. But until now, nobody succeeded in making a silicon-based laser. And that's what we are now doing in the SILAS project, and we are very close. And once we would have such a silicon-based laser, then chip-to-chip communication by light becomes a possibility. that you see here, say, in these two artist images at the top. And that might be a nice innovation opportunity. So let's look to the semiconductor industry. So currently, the semiconductor industry is subdivided into the electronics industry and the optical communications industry. And if you look to the electronics industry, then the workhorse for the electronics industry is really silicon. But silicon has an indirect band gap, so it can never emit any light. On the other hand, you have a growing optical communication industry with the internet, with all kinds of cloud data centers. And here the workhorse is indium phosphide. So indium phosphide is a direct band gap semiconductor which efficiently emits light. Now the problem is with indium phosphide that it's not silicon compatible. So there is not a scalable fabrication route towards fabricating indium phosphide on silicon devices. And that's a big problem. So the objective of the CELAS project is to merge electronics and optical communications using one new material. And that one new material is silicon germanium. So on the one hand, cubic silicon germanium is silicon compatible and it's already mainstream in electronics. No problem. On the other hand, we have hexagonal silicon germanium, which has been developed in the CELAS project. And hexagonal silicon germanium is an efficient light emitter. And it might be very useful for optical communications. So let's go to the basics. So let's look to the crystal structure. And if you don't know crystal structure, then maybe you have seen the atomium in Brussels. That's the crystal structure of iron. So here I show the crystal structure and the atomic arrangement of cubic and hexagonal silicon germanium. And the point is that if you have different atomic arrangements in these unit cells, you have different material properties. So what you then get is this, and this sheet is a little bit for people with a technical background, but the cubic silicon has an indirect band gap, so it does not have any light emission. But hexagonal silicon germanium has a direct band gap, and it has efficient light emission. So we think that we can make in the coming months, and we promised that in the CELAS project, that we can demonstrate a first laser. So these are the first silicon germanium nanostructures. So you should know that hexagonal silicon germanium has never been fabricated by anyone except in our consortium. And here you see we fabricated it with different material compositions. And once we have different material compositions, you see that we also have emission across a large wavelength range. So we have emission here at 3.5 micron with hexagonal germanium. So that's maybe nice for infrared optical sensors. And we can continuously tune the emission down to 1.8 micron, which is nice for optical communications across short distances. Now, if you look to the light emission efficiency, then we can compare the light emission efficiency of hexagonal silicon germanium with indium phosphide. And then you see that the light emission efficiency is comparable or even a little bit better than indium phosphide. And the light emission efficiency is way better than cubic silicon. Now, we deduce that light emission efficiency by photoluminescent lifetime measurements shown in the bottom, and that's again for specialists. So what are the future innovation possibilities? Now, there are many possibilities with a new material. So I will only mention a few. But maybe a very nice one is Moore's Law. Because you all know that Moore's Law had a growth in microprocessor performance for years. But now Moore's Law has leveled off. There's no growth anymore for single core performance. So what might be a solution? Now the solution might be to use many cores in a processor. But then you need communication between all these cores. And by electrical wiring, that's difficult. But by optics, that might be a possibility. So by optics, connecting all these cores optically, and there's already optical circuitry and silicon photonics available. And if you would do that, then every core operates at 2 gigahertz. The optical circuitry operates at 40 gigabits per second. So the optical circuitry can deliver all information exactly on time to the correct core of the processor. This might also be energy efficient. But there is one big problem. And the big problem is that the light source is missing. We don't have a light source which can easily be integrated with processor cores at the moment. And hexagonal zone germanium might be an option for that. It has at least the material properties to do it. Another possible application area are optical links in cloud data centers. So here you see such a cloud data center. And for the communication from rack to rack, they use already optical links. So here you see such an optical link. And these optical links are transmitting 400 billion optical bits per second. But the point is how to fabricate these optical links. Now, Intel fabricates them and they are more or less gluing an indium phosphide laser onto silicon. It's a very costly and not scalable process. So you can make maybe tens of thousands of these devices, but you cannot make 100 million of these devices. So for that you need, again, a silicon-compatible laser, which can be made in a scalable production process. Now finally, I like to discuss optical sensors. And one, yeah, my slides are very bad, sorry. Something changed, but one is on-chip LiDAR, which also needs many light sources. The other are lab-on-chip devices for sensing, for gas sensing, for biomedical sensing, pollution sensing, and so on. But each time you need then a cheap light source, because if you would see a large market, which is low cost, then the light source should be cheaper than which is currently available. And then you need a group 4 or a silicon-compatible light source. And that silicon-compatible light source has to be manufactured in a scalable process. And silicon germanium might be an option for that. At least the material properties are good enough for it, but we are not yet there that we can also integrate it. So this is the team, and you see all universities involved. Also IBM is a part of our consortium. And I would like to conclude that hexagonal zone germanium might be a very disruptive technology, and it can potentially revolutionize the semiconductor industry. So thank you for your attention.
Excellent. Thank you very much, Jos. We come to the last presentation in the new materials part of this session, and it will be given by Adélio Mendes. Adélio is Professor of Chemical Engineering at the University of Porto in Portugal, and he will explain us about a revolutionary new type of solar cells that are based on perovskites.
Thank you very much. Is it this one? Is good. So good morning to everyone, and I'm very happy to be here and to share with you some breakthrough achievements. So this is the project. It's working. Gathers together 6 countries and 7 institutions and 3 million euros funded by the European Commission. First was the dams to produce electricity. Then it comes also the nuclear energy. But coal, it's the energy source that is used mostly for producing electricity. It produces very cheap, at a price of around 5.5 cents of euro per kilowatt hour. In Portugal, this year, the photovoltaic electricity is 1.48 cents of euro. It's 4 times, almost 4 times cheaper. This is the so-called green revolution. So it's not any longer the fossil fuels that produce the cheapest electricity, but actually technologies that harvest sunlight, which is a renewable source of energy. But most of these photovoltaic panels, silicon, are produced in China because they need to produce in very, very large plants to be really profitable. So Europe was losing the leadership. We developed the most of the original technology, but this technology moved to other countries, other zones of the globe. Is it possible to bring it back? This is a story of success on developing new technology for photovoltaics. So everything started in 2009 when Miyazaki reported this seminal article reporting a new light absorber for photovoltaic cells, the so-called perovskite solar cells. It's a special type of perovskite, is organic metal perovskite. By the time was 3.8% the energy conversion efficiency. I should remember that for small devices, silicon performs at 26% power conversion efficiency. This new technology is different from silicon because the absorber layer is just 350 nanometers. You can see in red. 350 nanometers compares with silicon that is around 200 microns, so almost 1,000 times thicker. This is a very thin layer. And though it absorbs most of the sunlight and produces electricity in a very efficient way, that now, 10 years after, is 25.2% the world record. So the world record for silicon, crystalline silicon, is 26.1. This technology in 10 years moved from 3.8 to an amazing 25.2% conversion efficiency and still increasing. Now, target is about 30 or plus % on tandem devices. So when you have two cells stacked one over the other. So just about GOT Solar, which was the project that sponsored some of these advancements. Within this project, it was possible to demonstrate for the first time in 2006 stable devices, because before they were not stable at all. And for the first time ever, we described a device that is 21.6% efficiency, 1.24 volts, which is quite large and very close to the thermodynamic value. And it was stable at 85 degrees for more than 500 hours. But we want more. And first, it was absolutely impossible to glass seal glass cells to encapsulate these devices. It was impossible because if you have at edges of the glass substrate a glass frit and you fire a laser, for instance, the temperature goes above the melting point around 400 degrees or more and starts contracting because it's cooling down, gets adhesion, and obviously the shrinkage is higher than the substrates, which are colder, and you break everything. But eventually we solved this problem, and now we can glass encapsulate the cells at 85 degrees and below. And now we can go as fast as 1 centimeter per second on glass sealing. And moreover, we can put the glass sealing line just in one side of the substrates, the one that is going to cover it, because the other substrate is free to deposit all the layers necessary for the photovoltaic cell. This was really possible. So now you can see already a nice device that is almost ready for going to the market. And there are several companies. The company that was most involved in this project, Great Cell Solar, unfortunately has difficulties, financial difficulties. So the technology was really passing to them, but fortunately there are other companies taking advantage of these developments, especially concerning the glass ceilings. Several companies worldwide are interested on that, and there is in particular one company that is now developing the technology for laser ceilings, so to become commercial. There is one concern about perovskite solar cells. They can be made in small plants. They can be made in Europe, and they are cheaper, and they use less resources compared to silicon. But they have lead, the most efficient ones. But even this was also addressed. And now we developed, after the project being concluded, we developed a system that if the cell breaks, actually inertizes all lead inside. If goes above 1000 degrees, also get inertized. So we have no problems any longer with lead. And so I'd like to acknowledge all the partners and all the people of this project. Thank you very much.
Thank you very much, Adilio. And I would like to pass now the microphone to a colleague of mine, Jasna, who will introduce the next 3 showcases, right?
Thank you. So my name is Jasna Rešić. I'm a project officer, and I am project officer of some of these projects in Pathfinder, FET Productive. And now let's continue with the showcasing, exciting, in the areas of digital technologies. So I welcome to the floor Thomas Schmickel and Martina Copek from University of Graz. They're going to present not 1, not 2, but 3 projects. 4, okay. So Subcultron, Flora Robotica, Hivopolis, and the 4th one, Assisi. Okay, welcome.
So, I'm Thomas Schmickel. Hello, thank you everybody for coming. I'm really glad to be here. And I decided to take my chance and crash your party a little bit with a problem that is a very urgent one. And I would like, if I have many people who are in decision making and in this technology that I'm going to talk about, if I have them in the room, collected from all over Europe, I think I have a very, very important problem to make you aware of. So I will not speak so much about technology. Martina will do that in the second half of the talk. I will do the problem statement first. So my talk is named, Will Robots Save Nature? And you would probably ask why this nature needs to be saved. And I, as a biologist, I would give you the following answer. So this is when I started to study biology. This is what I wanted to do. I wanted to go to the rainforest and dive down in coral reefs and stuff like that. Or maybe even study, like say, original agriculture. And all of these things have one thing in common. They have a huge diversity. So in every few square meters, you find a lot of different ecological niches. But when you look at these places now, more and more over time, they will look like that. And you probably have been made aware in the last weeks of burning rainforests, for example, deforestation, but it's not only the rainforest, it's also other forests. Coral reef bleaching, dying coral reefs, and also when we look at agriculture, we see that a lot of the diversity is lost. Monoculture has only one ecological niche, which is only suitable for the crop that you grow and nothing else. So this is how we change nature, and we have done this since, I guess, 100 years at least, that we have massively changed the environment. And this problem has become so important that it's called now the 6th mass extinction in Earth history. And like a year ago, New York Times magazine picked up the story. They were not aware of the sixth mass extinction at this moment. They called it the insect apocalypse because like they realized that the insects are gone. And they told this in a nice story, which I remember from my own childhood. It was very much the same. And probably you remember the very same thing. When I was a child, I was driving home with my parents. We had a little garage, but not such a fancy remote garage opener. So my parents had to go out and open the garage. I, as a kid, was in the car. And after, I don't know, it took 1 minute, but it looked like that. Yeah? When I remember in my own childhood, when I looked at the cones of the lights, it was called like a snowstorm. Yeah? This is how New York Times called it, a snowstorm effect. Now, I own my own car now, and when I go home today, it looks like that. If I'm lucky, I have one single moth in my cone, and I remember, and probably you also remember, it was very, very different just a few decades earlier. So this is what is called the insect apocalypse, and very, very few people see it because it's very difficult to see that something is not here. Yeah? So this is a problem. So when you start studying biology like I did, you learn about the big five. The big five were the 5 big extinction events that happened since the origin of life. You see what died out in those big 5 moments. The 5th one was the dinosaurs. You're all aware about the dinosaurs going extinct. Problem is, we are here and we are currently facing the beginning of the big 6. Yeah? So we are actively producing something which is comparable to the extinction of the dinosaurs. We are in the beginning of that. So that means that many things die. Many things we depend on. You see the honeybee colony collapse disorder was very famous a few years ago. We see that happening in the marine world. And probably we are not seeing the real big scope of the problem because there is a lot of discussion about honeybee decline. Because this is what you see. If you are a beekeeper and all your colonies are dead, this is something that you realize. But the honeybee decline is maybe just a part of the big insect apocalypse. But even the insect apocalypse is not the whole story. It's part of the 6 big mass extinction. So probably we have a lot of things that we are afraid of. Yeah? And we are very often afraid of things. Maybe we should not be so much afraid of robots taking away our jobs in 150 years. Maybe we should not be afraid of sea levels rising in 100 years a few centimeters. Because probably we don't see the monster that's already waiting here. Within 1 or 2 decades, there can be massive ecosystem collapse. Already now, some ecosystems have lost 75% of all species and of biomass that's in there. 75%. This was happening within 15 years. In the last 15 years, some collapsed by 75%. So why is this suddenly appearing? Why is this rapid collapse happening? So now you get a short story in biology, and then we see what robots can do about that. So if you imagine you have one plant, doesn't matter which one, and you have another plant, and there is some relationship between these 2 plants, so they interact with each other. And let's say you have one type of animal, which depends on the one plant, and you have another animal, which depends on the other plant. Yeah? You can imagine, it doesn't matter which ones they are. As soon as the one animal has any sort of interaction with the other animal, something appears here in the system. You see now that you can follow all these arrows in one circle, and this is what we call a feedback loop, an ecological feedback loop. And these feedback loops, they are stabilizing ecosystems. This is the most important part in ecology, that we have those feedback loops. But think about one of these guys here goes extinct. It just disappears. Then the problem is not only the guy goes extinct, also the arrows disappear. And now the feedback loop is gone. And without that feedback loop, the stabilization is gone, and so over time also the other guys will disappear. And this is what's going on currently, that we have this cascade effect in ecosystem, which is promoting species for going extinct. Question is, what could robotic agents do? How could we use robotics, autonomous robots, for buying us some time, helping with this problem, and actually trying to get us to survive? And thinking on that, we came up with a plan like a 3-step plan that we are developing, and like all the projects in my lab go along that line. Step number 1 is monitoring. So if we have autonomous robots, then we can use them for actively monitoring ecosystems and see, oh, something is going wrong there. You will see one project presented by Martina about that. Second step, if you already have robots and they observe something is going wrong, well, you have your robot there. So you could interact, you could make a local small-scale repair act. Just try prevent things from going worse. And the third step that we are approaching, we call this ecosystem hacking. That's more like a strategic large-scale approach, a global approach of actively trying to stabilize ecosystem by having an overall picture. So how we are going to do that, Martina is going to present.
Thank you, Thomas. So I'm starting with a project that is, let you out. Okay, so first point, monitoring. We're starting in Venice. Everybody knows about the Venice Lagoon. Everybody has nice pictures in mind when they're thinking about Venice. You have the canals. It's really nice. It's quite picturesque. So what we're doing there with our robots for monitoring ecosystems. This is how the lagoon looks like in reality when you're not only there as a tourist. So it's a very harsh, very complex, very structured ecosystem that is very hard to monitor because of the circumstances. So our approach was a bio-inspired one. We developed a swarm of robots, or a society of robots that is not only comprised of one robot, but of very different robots with different abilities. So the first robots are these iPads. They are inspired by lily pads. Those are the ones on the surface that can link to the humans, that are able to power the other robots. They can dock with the other robots. They can taxi them around. So this is the global link to the above sea world. Then we have the A-fish. There are 25 of those. Those are inspired by the elephant nose fish. The elephant nose fish is a small weakly electric fish that can navigate and find prey in very structured environments by electric sense. So this is what also those robots can do. They are agile, they have electric sense, they can navigate in muddy waters, in structured environments, and are the information carriers between the other robotic devices in this swarm. And those are the A muscles. The 120 A muscles are the sensing units. They go to the seafloor, they can stay there for a long time, autonomously collect data, get the data to the A-fish, and then also get the data to the A-pads and to the human operators that can then read out data and get alerts about any environmental changes that are perceived by those muscles. They are inspired by razor clamps. You can see them on the right side. Because I'm going to present a few projects, I only have little time, so I'm not presenting all the robotic devices, just that you see how this little fish reacts in its structured environment. It does not work? Yes, it does. So this elephant nose fish. It lives in very structured environments in African rivers. Here the water is clear, but it wouldn't usually be. And this little guy is navigating quite successfully in that environment. And if you see one of our A fish here, so the goal here is to go from one of these A muscles to the other and transport information, and it's just using electric sense to navigate here in this pool, and it's doing quite nicely. And here you can see one of those in the Venice Lagoon. So these are the actual circumstances those robots have to operate in. So it's muddy, just vision wouldn't help much to navigate. So going on, Thomas was mentioning, after we are able to monitor with robots, it would be nice to be able to interact with the environment, with living beings around. And one of the projects was Flora Robotica. And this project aim was to develop a society, a biohybrid society of plants and robots. So it's not only able to influence and interact with animals, but also with plants. And you can see here a little bean sprout. And the goal was that those little robots that you see on the upper right can actually interact with the plants growing, can guide the plant to different targets. So the robots are actively influencing the growth of the plant. This is done by observation first, then the models in the robots adapt. The actuators, you see them here with light, so every time the robot on the right turns on the actuators, it's the light blue line, and every time the robot on the left is turning on lights, it's the dark blue line, and together they can react to the plant growing and can intervene with how the plant grows. And because it's our specialty, and Thomas was talking about honeybee losses, colony losses, we do a lot of research on honeybees. And this was the project ACCBF with the aim to develop a biohybrid society of animals and robots, where we really close the loop, where those little robots are able to interact with the bees, to sense the bees, and to have actuators that the bees react to in a controllable way. So those robots do not look like bees, they cannot move, but they can interact with the bees by using physical stimuli. Also the bees use like very light airflows, like wing beats. They can use temperature, like nurse bees that heat up. And they can use vibration, which is also a cue that honeybees use in their daily communication. And here you see the whole array of robots that was designed in this project. And this is just a showcase where we put in a lot of bees, and we wanted to guide them to a certain area. And over time, you will see the bees are running around randomly. And in the end, so the robots are, in that case, heating up a little bit to attract the bees, depending on what is around them. And in the end, you have the bees in a certain area. And from there on, so we knew how to monitor with robots. We now know how to interact with animals and also with plants to manipulate also their decisions in some way. So the newest project is about ecosystem hacking, which is called Hyphopolis. It's only running for around 5.5 months now, so no fancy videos yet here. But that you get the concept, it's about smart city for bees. So bees have to face a lot of threats, have a lot of man-made things to face, from the change, the global change, to various parasites that we introduce, to beekeeping in a fashion that is not very bee-friendly anymore in some sense. So the idea is to totally redesign how honeybee hives work, how we work with honeybees, to go for a very modular design with different compartments that can help and aid the bees in their daily lives, from helping them in the brood rearing, to being able to harvest just little amounts of honey without disturbing whole honeybee hives, to really get the honeybees in the urban environments, but also in a way that they do not interfere with natural pollinators. So we really want to steer the bees in a certain direction that is not only beneficial for us, but also beneficial for the animals. Just a few concepts that are very new. So we are going for new designs, new materials. This is a 3D printed outer hull that is biodegradable. It's wood filament. The idea is to replace any plastics like styrofoam with mushroom mycelium that is grown, that is also beneficial for bee health. We are going for population control by introducing temperature sensors and temperature actuators. They can draw energy that is produced somewhere else in the hive and aid the bees in cold weather conditions, for example, so that they do not have to use their own honey, so it's energy saving for the bees. We want to go for a really good health assessment, so we want to be able to monitor the larva, the growth, to detect any parasites, any illnesses that the bees could have very early, so that the system can also autonomously react to it. And one thing we want to work on is traffic control in hives that makes the management of hives easier, that also might draw private, more hipster-like beekeepers to beekeeping that are now probably afraid to get stung, so to really introduce honeybees into urban environments. And with that, I would like to give back to Thomas for the wrap-up.
Okay, thank you, Martina. So at the end, we were thinking, what do we need in order for get this going and further promote robotics, autonomous robotics in this field? And when it comes to monitoring, I think there are a few research topics that are very important. We should look for a large-scale operation in robotics out of the lab in the wild. Usually most robots run in a factory or even in a robotics lab, so that's not something that you can use to monitor ecosystems. So there should be way more projects bringing out their robots into the wild and having them run there. Long-term autonomy is of course important. In order to achieve that, it should be investigated whether robots could do energy harvesting to support their own living. This way robots will become closer to animals, of course, because they will feed on the environment just like animals do, and also need to do energy saving. They have to be robust for surviving long, but they also have to be flexible, so not getting trapped into deadlock situation. And of course, if we release robots to the wild, sustainability is important. So we don't want to further pollute the environment. So we have to think about the life cycle of these devices, how we get them back, how we can 100% remove them from the environment after the job again, or even better, if we could produce biodegradable robots that actually can just fall away or something like that. Yeah? So second, interacting with the environment, we need to have biocompatibility, so we need biocompatible materials for that, behaviors, sensors, actuator. So everything in these robots has to be designed in order to be compatible with the environment, with the organisms they have to interact with. And finally, when it comes to ecosystem hacking, so actually they should interact with animals, maybe even replace animals. So suddenly a topic in robotics which was always very, very difficult to justify, biomimicry. Why do we have so many snake-like robots, fish-like robots, spider-like robots? Yeah, so we have done this hundreds, thousands of them in the last decades. Now, for such a topic, for such a design and mission that we suggest here, biomimicry is suddenly a very important factor, and we have probably to go to high population sizes, maybe even self-reproducing robots, which is a sort of holy grail, of course, in this field. So thank you for listening. All of that would not have been possible without FET, without support from the EU, and the many partners that we had in the past decade in doing all of that research. Thank you.
Thank you very much, very interesting. And now we come to the last but not the least presentation for this session. Welcome to the stage Mr. Stephen Burster from University of Glasgow. He will present Levitate.
Hello everyone. So last project is the Levitate Project. So I'm from the Computing Science Department at the University of Glasgow. We have partners from Germany, Sweden, and from the UK. We have one company. So this is mostly a kind of computer science and engineering project with an underlying theme of acoustics. So what are we trying to do? So we are trying to create, prototype and evaluate a radically new human-computer interaction paradigm that allows the unadorned user to reach into a new kind of display composed of levitating matter. That sounds quite complicated. The thing we're trying to do really is replace the kind of pixels that you might see on a screen like this, on a huge screen like this, each one of these individual things there's millions of them. We're trying to replace those and create physical displays which are made of physical pixels that then we can generate a real 3D object in front of you as you require it. Then it goes away when you don't need it anymore. You can change it, you can create it from scratch from these individual physical pixels. So, how does it work? Well, actually, the technology to do it is somewhat straightforward. Those things there, they're what you have in the back of your car or in the front of your car bumper so that you don't reverse or drive into a wall. So these are ultrasound loudspeakers. So they're standard electronic components which we use in a kind of different way to the way they're used in cars. So if you remember from your school physics, if you have two waves propagating through the air, they can combine and create either stronger or weaker wave fronts as they go. So by combining these arrays of these loudspeakers and very carefully controlling the timing, we can make pressure waves in the air that you can feel. So you can put your hand in the air and you can feel them. If you want to see what it looks like, You can't easily see pressure, but using this, this is called Schlieren Imaging. It's a kind of special way of photography. You can see these wave fronts here. And you can see when we put the object in, you can see the reflections coming off the waves. So those are the sound waves which we've visualized. So they're sound waves in air. So there's two main things that you can do with it that we're doing with the project. The first one is haptic. So using the sense of touch, you're probably familiar with that from, you're holding your mobile phone and it vibrates when a message comes. So the interesting thing about this technology is it allows us to do non-contact haptics. So I don't have to be holding anything in order to get the feedback. I can have my hand over the array of things I showed before, and we can beam haptic feedback to your hand. So you can feel it wherever you are in that space. So then we can do things like interacting with your devices, and we can create virtual controls, for example. So maybe above my phone, I can pop up a control if I want to do something, and it can disappear again. So I can feel these things in space. I can create texture, I can create roughness, and then I can have it when I need it, and it can disappear again. So that's one part. The next part, probably the more interesting part, is that we can use those forces for something different. Instead of just feeling those forces with our hands, we can then use them to support small objects in the air. In our case, we're using small polystyrene beads, the kind of stuff you get in a package if you order it from Amazon or something like that. So we use those as our physical pixels. So instead of having pixels on the screen, we have small physical beads. I'll show you pictures in a minute. And from those individual pixels, we can combine those into complex 3D shapes. So in the same way that you might create things that look like characters on the screen there, we can create physical 3D shapes. Here's a very early prototype that we did on the project. So you can see these white dots here. They're the polystyrene beads. This is an old one, so the arrays are very small, but you can see top and bottom. There's two small sets of those things you have in the back of your car. And to show that we're not cheating by having them on strings or anything, we can put those beads in, hold them in place, and move them around. Now, the nice thing about ultrasound is you can focus the sound waves very precisely, and you can control the sound field very precisely, so that we can put those beads in, we can hold them stably, and we can move them around. So here's another version, a more recent one. So this time we've got a much bigger array. So here we've got the corners of a cube, and we can then rotate them around. So this is beginning to show that you can create these solid objects in space. Now, perhaps we're a little bit like it was in the 1960s when somebody got an oscilloscope and showed, look, I've made a pixel on my oscilloscope, and they could maybe do 1 or 2 pixels. So for now, we're starting small and then starting to increase the number of pixels. So at the moment we're looking at, so how can we control the sound field to do the manipulations you would need to control objects? So here we're rotating in a different dimension. This one is much more complicated to do because of the way the sound field works. You're moving in and out of the sound field in a different way. So you can see in this case, they're a little bit less stable in their movement. But we're building up the techniques in order to control the pixels and move them around as we would need. So displaying them is one part, but we also need to do some interaction with them. So imagine that I'm creating a model of something in space in front of me. Maybe it's one of these. I want to be able to interact with it. If I'm a designer or something, I would like to be able to deform it, change its shape, manipulate it. So we're using in-air gestures, as you can see, Ewan, one of the postdocs there. You can see doing gestures to control the pixels. So in-air gestures to control the pixels. We can also do haptic feedback onto his hand as well with the same array. Other interesting things that you can do with it is you can use the ultrasound haptics and the ultrasound levitation with other objects, if those objects are acoustically transparent. So this is felt, and it's on a wire frame. Those things are acoustically transparent. So you can use the haptics through other materials, and you can use the levitation around other materials. So it's a way of taking existing materials and making them interactive in ways that they weren't before. I'm not exactly sure what the use of those two tubes would be in real life, but it gives you the idea that you can control and manipulate them. You can move the beads through those. You can transport things in ways where you don't need to touch them, for example. So, Levitate Project. So our idea is we're going to create a whole new form of interaction with pixels. So these are physical pixels. This is not something on the screen. This is something, a real object that would be raised up in front of you. We could share it. We could look at it together. We're not doing tricks on a screen to simulate 3D. This is the 3D object. You're perceiving it in a way that, it's in the same way you'd perceive any other solid object. The tricky part of the project is we're looking to combine levitation and haptics in one array. And also sound. Because these are loudspeakers, you can also do sound, of course. But combining all of those together in the same array at the same time is extremely difficult in terms of the timing, in terms of the design of the sound field. So that's very complex, and that's something that we're working on right now. But if you can do that, you can then have things you can see, you can touch, and you can hear all from one array right in front of you. So the really key thing here is that we're going to use this for new ways to understand data, manipulate information, create 3D models, physical things that you can actually look at and manipulate in front of you. And so that's the aim of the project. So we have partners, so I mentioned we have partners from University of Glasgow, University of Bayreuth in Germany. We have Chalmers, and Ultraleap is the company that is making those arrays that I showed. Thank you very much.
Thank you very much. So thank to all of the speakers. And now I will invite you to go to our future board so we can showcase all of our projects here. We have a lot of interesting project results. So I invite you just go outside to the right. It's going to be a big future board screen, and there you can see other results of other Pathfinder projects. Thank you very much.